We're going to talk about normal vectors and surface area for parametric surfaces. So back in chapter 14, we talked about a method for using a double integral to find the surface area of a surface. So if we had our surface z equals f of x, y. We used a cross product of we made vectors out of partial derivatives. Components of our vector had to do with the partial derivatives with respect to x and y, and we took the cross product of those vectors to come up with an expression for a surface area. And we said that our surface area, we ended up with a double integral. It was a double integral over our region of ds, and we said that ds, our surface element, was f sub x squared plus f sub y squared, partials with respect to x and y, plus 1, and we took the square root of that. And again, this came from looking at tangent vectors to the surface, and we approximated the area of the small little parallelogram of area on the surface by the magnitude of the cross product of the two tangent vectors. So we can use a similar argument to come up with an expression for the surface area if we have our surface given by parametric equations rather than an explicit equation. So what we're going to do is we're going to look at this little piece of surface, just like we did back in chapter 14, and come up with a way of finding our surface area. So here is our surface, our generic surface, z, x, and y, and we're going to look at a curve in one direction and a curve in the other direction, not necessarily in the x and the y direction. And we're going to think about this normal vector to our surface. And we said that for a parametric surface, we have r of some parameters u and v, and we're going to say that's, and I'll just write it this way, h of u v I hat plus g of u and v j hat plus, I'll just call it g, h, and p, u and v, I'm just making these up, v k hat, just some functions of u and v for our components. So if we take the partial derivative with respect to u, we get a tangent vector in the direction of u, and we can take the partial derivative with respect to v, and we get a tangent vector that points in the v direction. So we're saying these curves on my surface are in the u and the v direction. And my surface here is r of u and v. So we're going to take our partial derivatives. That's going to give us a tangent vector at a particular point, a tangent vector that points in the u direction, and a tangent vector that points in the v direction, whatever u and v happen to be. And our normal vector is going to be given by the cross product r sub u cross r sub v. And the curve here, again, the curve that we're talking about here, this is where u is constant, sorry, v is constant here and u is constant here. So we're taking our partial derivatives in the u and v direction. If we make our little, we're going to divide this into little rectangles. So let's magnify this. Magnify this little rectangle. So we have a little piece of surface like so. I'm going to say magnify. So we're zooming in. And here's my tangent vector here, r sub u, and here's my tangent vector here, r sub v. And we're going to call this delta v. And this distance here, delta u. So we have one small rectangle. So we're dividing our surfaces into these small rectangles. And we have our tangent vectors there. A normal vector is given by the cross product here. And if we let the increment, the delta v and the delta u, get very, very, very small, we're going to use the same argument that we did in chapter 14. We're going to sum the areas of these small portions. The area of that small portion, if we form the cross product and take the magnitude, the area is approximately the magnitude of the cross product times delta u delta v. And then we let the delta u delta v get very, very small. We sum those areas over the entire surface, and we get an expression that is a double integral for the area of that surface. Our area is going to be the integral, double integral over our region of the magnitude of the cross product of these tangent vectors, du dv. And we could also write this, and this will be useful at times, the magnitude of the normal vector du dv. So we take these little rectangles, approximate the area with the magnitude of the cross product, let delta u delta v get very, very small, sum that over our surface, and we get our double integral for our surface area. And if z equals f of xy, so we have our explicit form for our surface, then, like we said yesterday, then our parametric form of this surface would be xi plus yj plus f of xy k hat. And this surface integral, the area, surface area, this double integral reduces to exactly what we talked about in chapter 14. The cross product, we end up with just exactly this quantity for the magnitude of our cross product. So our expression for our normal vector and for our area are for a smooth surface. And that's telling us that the cross product r sub u cross r sub v is not zero on the surface in any points at any point in our region. So this gives us a way to find a normal vector if we're given a parametric surface, and it gives us a method of finding the surface area of a parametric surface. And what we're going to do with this idea of the surface area and our normal vector is we're going to extend that to finding a surface integral. So a surface integral is a lot like we did with a triple integral or a double integral, where we're going to take the value of the function at any particular point on the surface and sum that function value over the entire surface. And one of the things that we're going to be interested in is summing the normal component of a vector field over a surface. So that's where we're going with this idea.
Mr. Beaver?
Yes.
What happens if the cross product is zero?
Then we would have to we'd have to redefine our region. So to take, basically we're kind of removing that point from our region. So it's kind of like it would kind of be like what do I want to say? An improper integral, where we have to make our boundaries around that point and deal with that separately. For what we're going to be doing, we're going to be talking about smooth surfaces, and we don't have to worry about that happening. All right. So I want to look at a couple of examples of working with these ideas of finding a normal vector and the different types of things that we would do with a normal vector, and an example of finding the surface area of a parametric surface over a specific region. All right, are we good so far? Okay. So one of our favorite things to do with a normal vector is find an equation of the tangent plane. So we want to find an equation of the tangent plane. That whenever we see the question find an equation of the tangent plane, we should think we need a normal vector. We need a normal vector to write the equation of a plane. To our surface, R of u and v is ui hat plus v j hat plus the square root of uv k hat at 1, 1, 1. So equation tangent plane, that should tell us we need a normal vector. So we need a normal vector. Well, we know how to find a normal vector to this parametric surface. Our normal vector n is going to be r sub u cross r sub v. So we need to find our partial derivatives. We take the cross product at 1, 1, 1. We'll get our normal vector. And what does our normal vector give us for our tangent plane? What do we need the normal vector for to write the equation of our tangent plane? Our direction numbers. We need our direction numbers for our tangent plane. All right, so let's form our partial derivatives. R sub u. If I take the partial derivative with respect to u, I get I plus 0 j plus, what do we get, v over 2 square root uv k hat. And r sub v, when we take the partial with respect to v, we get 0 I hat plus j hat plus u over 2 square root uv k hat. And we'll form our cross product. Our normal vector is given by the cross product of these two. So we'll make our cross product. I always have to write out my cross products or I make arithmetic errors. And so when I form my cross product, I get I times 0 minus, I'm going to write out all these things, v over 2 square root uv minus j, just writing out all the components, u over 2 square root uv plus k hat times 1. And then we want our normal vector, we're looking at 0.111, so our normal vector of 111 turns out to be negative 1/2 I hat when I substitute in 111. When x is 1, u is 1, v is 1. When y is 1, v is 1. And we don't have to worry about the z. And we have a minus 1/2 j hat plus k hat. So now we have our direction numbers for our tangent plane. So our direction numbers. So A is, I'm just going to use these directly. We could multiply by 2 if we wanted. A is negative 1/2. B is negative 1/2. And C is 1. And we know that we have 0.111 is on our tangent plane. We want 0.111 to be on our tangent plane. So our equation of our tangent plane is minus 1/2 x minus 1 minus 1/2 y minus 1 plus z minus 1 equals 0. Or I could rewrite that as x plus y minus 2z equals 0 if I distribute and simplify. So that would be the tangent plane to this parametric surface at 0.111. And this normal vector is going to be important for what we do with surface integrals, what we do with the divergence theorem, what we do with Stokes' theorem. Normal vector to a surface is a pretty important quantity. All right, questions on that example? All right, so let's look at an example of finding a surface area. Of this surface R of u and v equals square root of u cosine v I hat plus square root of u sine v j hat and plus u k hat. And we want our surface area in the region 0 less than or equal to u less than or equal to 4 and 0 less than or equal to v less than or equal to 2 pi. So looking at this, anybody have an idea of what this surface would be? The paraboloid? Let's see, x squared plus y squared equals z. Yeah. So it would be a paraboloid. This would be a paraboloid. Parametric representation of a paraboloid. All right, so what we need to find our surface area, we need to find the double integral over our region of the magnitude of r sub u cross r sub v du dv. That's our surface area integral. So we need to take our partial derivatives form our cross product and find the magnitude of that cross product. So a little bit of work to do here. So let's find our partial derivatives. Partial derivative with respect to u. When I take that partial derivative, I get cosine b over 2 square root u I hat plus sine b over 2 square root u j hat plus k hat. Our partial with respect to v, we get minus square root u sine b I hat plus square root u cosine b j hat, and we get no k component here with our partial with respect to v. Now we need to form our cross product. So let's write out our cross product, r sub u cross r sub v. So we get this determinant ijk. Cosine b, 2 square root u here, sine b, 2 square root u, and 1. And for our partial with respect to b, minus square root u sine b, and square root u cosine b, and 0 there. So we have this nice cross product that we need to deal with. So when I do this cross product, I get I times I hat times minus square root u cosine b minus j hat times square root u sine b, and plus k hat, and I get a nice k component here. Let me expand this way. Cosine squared b over 2 plus sine squared b over 2. And when I simplify this, I end up with, I'm just going to rewrite this. I get minus square root u cosine b I hat minus square root u sine b j hat plus 1 hat. So I have a nice sine squared and a cosine squared. Now we need the magnitude of this cross product. So we need, our integrand has the magnitude of the cross product. So I find the magnitude of this, RU cross R sub b. So that's going to be the square root of u cosine squared b. This is starting to look a little nicer. Plus u sine squared b. Looked a little intimidating at first. Plus 1/4. And this simplifies to square root of u plus 1/4. So now we have our integrand. So this is not going to be a tough integral. It'll look like it could be ugly when we saw all these things. Look like it could be a messy integral, but this turns out pretty nice. Not too bad here. So we're going to integrate this over our region. So our surface area integral is an integral over our region of this quantity, du dv, and u is going from 0 to 4, and v is going from 0 to 2 pi. So we have a nice integral, so I'm going to go to the next page for our integral. So our surface area is going to be the integral from 0 to 2 pi, the integral from 0 to 4 of the square root of u plus 1/4 du dv. And here we just have a nice u substitution. U is just, we would do u prime sub, I guess, since we already have a u. So we have a u plus 1/4. So our du is just du. So we just have a u to the 1/4 to the 1/2 power. Epsilon sub, epsilon and delta sub.
Yeah.
0 to 2 pi, we end up with 2/3 of u plus 1/4 to the 3/2, and we're evaluating that from 0 to 4, and this is going to be a dv. And when we evaluate this out, so this is, I'm just writing this out, the dv is just going to give us a multiple of 2 pi times whatever we get here. So we end up with, when we evaluate this and simplify, we get pi over 6 times 17 square root of 17 minus 1. And that's approximately 36.18. So our surface area over that region is about 36.18 square units, whatever our units of U and V were in. All right, questions? Well, thankfully from here on out, really, we use the idea of a parametric surface to introduce this method of finding our surface area, the cross product of our partial derivatives to give us our normal vector. From here on out, we're really going to be working with surfaces in explicit form, so z equals f of x, y. But we will use some of these tools that we developed for parametric surfaces to come up with some expressions as we move on with surface integrals to get to the divergence theorem and to get to Stokes' theorem. All right. Homework. There you go.